Okay, welcome everybody to session 6 of the Groundwater Mentorship program. Yeah, this will be the last sort of technical presentation we'll do for a bit. We'll go back to the general stuff from Thursday, just to give you guys a bit more exposure to what we do rather than how we do it. In this session, we're going to go through the sustainable yield determination, which is part of your aquifer testing, but it's more also part of your licensing and the overall processing for a borehole. Yeah, we'll go through just the Groundwater Project, just to remind you guys to check that out. And then the online schedule, just to remind you guys where we want to go from here. And then the 3 main sections we'll go through tonight is the borehole yield calculation, safe yield versus sustainable yield, and then the sustainable yield calculation. Okay, so Groundwater Project started with the Hydrogeology Without Borders website, where they're trying to share and publish groundwater educational materials free of charge. You'll see today on LinkedIn that they're going to release a new sort of proprietary book or unique book to Groundwater Project on the groundwater cycle, which will be worth looking at. Yeah, if you guys haven't followed them already on social media, I suggest you do that and register on their websites as well. It's a really worthwhile program that they're running. In terms of the schedule, yeah, today we're doing the aquifer testing. We're extending on the sustainable yield, which we didn't do last time. So session 6 on this slide will become session 7, which will be on Thursday. That'll be the groundwater characterization, what to look for, what's important and when it's important. Yeah, that's in terms of what kind of project you're doing. And then we'll focus on the conceptual model development, which is quite an important part of any groundwater study. Yeah, whether it's a resource development project or a mining project or any kind of groundwater project, the conceptual model is very important for your results. Then in August, we'll focus on groundwater modeling. We'll go through it at a high level. Types of the models we use, the model applications that we do typically, selecting your model, what sort of parameters you need to consider, then the modeling process, and then compiling your modeling report. Is there any suggestions for another session after groundwater modeling that you guys can sort of think of that you would like to see and be a bit exposed to?
Matthew, can we do something related to mines, like, you know, the mine water decanting, the whole process?
Okay.
Groundwater related in a mine, if that's possible.
Okay. Yeah, and I think Lazelle can also contribute to that one. Yeah, with your masters, Lazelle.
Yes, I did pit lakes on coal mines, which is essentially decant from open cast operations. So yeah, I know a bit of the chemistry and so on.
Yeah, well then let's make that sort of session 8 or whatever it works out to be. We'll do mine hydrogeology. Okay, thanks. Any other suggestions on what you want to be exposed to, guys?
Hi, Matthew.
Hey.
Maybe groundwater monitoring and management.
Okay. In terms of what exactly, like the design of the network or the execution?
Like everything, because I haven't really been exposed to the groundwater monitoring part of hydrogeology.
Okay. Okay, I'll give it some thought. Yeah. So monitoring and management.
Yes.
Okay, cool. Anybody else?
Hi, Matthew.
Hey, Victor.
I just want to sort of like just a suggestion that when you do the modeling, can we also sort of like have a scenario where we go and collect data and come back with it, incorporate it to the model software, and then sort of like get a result, maybe in sort of like a situation where we have groundwater surface water interaction, or rather modeling about contamination plume movement?
Look, it's very difficult, Victor, to do that kind of thing, because modeling is such a complicated sphere. Yeah, I can give all of you guys the same question and the same data sets, and you could give me 10 different models, and none of you could be wrong. So I think let's look at it on Thursday. I do want to get back to the exposure side, and then if you guys have specific questions, we can deal with that. But modeling is it's a complicated thing, Victor, so it can end up taking a lot of time.
All right, Matthew.
Have you done modeling before, Victor?
Yeah, I'm just exposed in, like, we have your mod flow. Yes, I'm just a bit familiar with mod flow. So, and yeah.
Okay. Yeah, look, we'll go through it on Thursday, and we'll see what comes out of it. But for now, I think let's just keep it high level, because modeling is not for everyone, and you don't have to worry about becoming a modeler. You know what I mean? If you don't get it or you don't like it, then it's not the end of the world. Okay, we've got a suggestion from Antonio just to focus on hydrogeology and underground mines and tunnels. We'll do a section on that as well, because that's quite an interesting one. Okay, so that takes us up to session 10 then. Any other suggestions? Rachel, any suggestions?
Sorry, I was just unmuting. I'll think about it and let you know. This is my first session joining, so.
Welcome. I hope it's useful. Okay, guys. I think let's carry on then. If anybody has something, you can just stop me, but we'll carry on. Okay, so first step we're going to do is the borehole yield calculation, which is from your pump test data. So I've done my pump test, and now I want to determine what recommended pump yield I should use for the borehole. So there are equations for the sustainable yield by the AENV. These are quick and dirty calculations. Yeah, the first one is your yield Q is 4 pi transmissivity, your available head, and a safety factor between 0 and 1. So think of this as a percentage. So make it 0.1, like a 10% safety factor. It'll take this number multiplied by 0.1. So you're being ultra conservative. And then here's another equation where your sustainable yield is related to your conductivity multiplied by the aquifer thickness, which gives you transmissivity anyway, multiplied by your available head, your static water level to the water strike depth, and then your safety factor. Oops. Yeah, the assumptions on these is that the aquifer is homogeneous, isotropic, fully confined and infinite in radial extent. Top and bottom boundaries of the aquifer are horizontal, flat, and impermeable. And the borehole is fully penetrating and does not take wellbore storage into account. Yeah, does that look familiar to anyone? No. Shocking. These are similar to your Cooper-Jacob assumptions that we did last week. And you can see the 4 pi t is coming out of Cooper-Jacob, your t available head. So they're very similar equations. But here is the PDF. I recommend you download it and have a read through it. But this is a quick way to get your sustainable yield. And the typical way we do it in South Africa is through the FC program, which is the flow characterization program from Free State. This comes out of the report that Gerrit van Tonder and them wrote about aquifer testing or sustainable yield determination in fractured rock aquifers. So you start off, is there any information about the abstraction borehole? If not, you study the borehole log and you conduct a calibration test, which gives you a rough idea of what's in there. And if there is available information, does that include the blow yield and the main water strike or other water strikes? You remember we spoke about the importance of your hydrogeological log in the previous session. So this helps you with your sustainable yield determination. If that's not available, then you need to do a slug test or a calibration test just to get an idea of the order of magnitude of the aquifer parameters. Once you've done that, you go onto your aquifer testing program. Which consists of your step test and then your constant discharge rate test. Yeah, that's according to the SANS 10299 in South Africa. Yeah, so the sustainable yield is defined as the rate at which water can be abstracted from a borehole over a long period of time without negatively impacting on the aquifer and or reaching the specified allowable drawdown point. For example, your main water strike. Does that definition make sense to everybody?
Yes, it does.
Yes. Yes.
Yes, okay. So you can't take more than there is. Okay, we typically use FC, like I said. This is the website link for the program. It'll download a zip file with the Excel spreadsheet. And then here is the manual on pumping test analysis, the WRC report by Van Tonder et al. From 2002. This is a direct link to that. Otherwise, you can just go on the WRC website and search in the Knowledge Hub. You'll get to this. It's a useful manual. If you couple this with your Chrysamon and Derrida that we spoke about in the previous sessions, that's definitely worthwhile. A question here, calculate the drawdown radius from Antonio. Antonio, I'll get to that just now because that's related to your Cooper-Jacob. So I'll just show you that in the Cooper-Jacob. Okay. So the guidelines to choosing your available drawdown. Yeah, we mentioned in the previous slide that your available drawdown is important for your sustainable yield. The way you choose your available drawdown. Does anybody have any suggestions? How do we determine the available drawdown?
Okay, there's sort of like many methods that you can use. Mm-hmm. And there's a one that you have to use sort of like a geometric mean when you don't have an idea of where is the water strike. So sort of like you just have to calculate a bit about geometric mean when you have your static water level and the depth of the pump and something like that.
There we go. So geometric mean between your maximum possible drawdown, which is your pump setting, and then your static water level. Okay. The position of the main water strike if you reached it during the constant discharge test. Yeah, Antonio says the point of inflection on the graph, the drawdown graph, which is correct, where you get a sharp increase. So where you start dewatering your borehole. Then in the event of a possibility of clogging, you're going to do it to the position of your first water strike. That's where you've got high iron content, high biofouling potential, something like that in your groundwater. Then if your borehole recovery flattens in late time in your recovery test and the borehole doesn't recover to the static water level after a time equal to that of the constant discharge test, the available drawdown should be adjusted to accommodate this difference. So for example, if your static water level is 24 and your borehole recovers to 26 meters, then you need to minus whatever you calculate your available drawdown, you need to minus 2. Does that make sense to everybody?
Yes, Matthew, it does.
Awesome. Okay, and then in dolomitic aquifers, rule of thumb, you take 5 meters as your available drawdown. That's just to prevent sinkholes forming. Yeah, this is just sort of a rule of thumb according to Fontonda in the 2002 paper. That's where you've got your 1,000+ transmissivities and that kind of thing. Okay, let me show you the FC program. Okay, can everybody see my Excel sheet now?
Yes, sir.
Okay, great. So this is the main menu of the FC program that you can download on that link. So you can see I've got data, diagnostic plots, derivatives, Cooper-Jacob sustainable yield, derivative sustainable yield, Barker analysis, step test, slug test. You've got a slug test interpretation there, and then the summary. So the ones we typically use is your data. This is the example that you download. So you fill in all of your borehole data here, borehole name, and then this one you physically fill in. And you can see here it's calculated your recommended available drawdown as 16. And then you fill in here based on the recommendation. You know, sometimes you'll put in a water strike distance of 24, but it'll still recommend 10. So then you can choose, do I want to take mine or do I trust the program? Then your extrapolation time. Yeah, minimum 2 years, but you can set it as 20 years, 10 years, depending on the life of your project. If you've got a farm that's going to be productive for 20 years, then set this extrapolation time as 20 years. Because remember, the definition of sustainable yield is where it can sustain this yield over time. So the longer the time, the more conservative you're being. Then this is your abstraction rate during the pump test over here, your drawdown data, and your recovery data. Leave these gray cells alone. These are the calculation cells. Everybody comfortable with the data entry in FC?
Yeah, thanks.
Cool. Okay, then you can go to your diagnostic plots. I don't know why it keeps telling me that. But then you've got your one-to-one line here to measure your one-to-one gradients. And you've got your what's this one? About 1 to 4 here, so your 0.25 gradient. And this is your 0.1 gradient. And you see there, that fits on that curve. Okay, we'll go back to PowerPoint just to explain. Well, let me show you the derivative graphs again quickly. So here is my data on a log diagram. So there's my raw data. Then here's my first derivative data. Okay, so what this shows is that is my fracture being dewatered, fracture dewatered, fracture dewatered, fractures dewatered. You see there it says log derivative is a good fracture network. So just remember this because I'm going to go back to the, yes, Klingiwe.
Matthew, can you just please explain why the derivative the low points mean that the fracture is dewatered?
I'm going to get to that. I'm going to go back to PowerPoint just to explain that. But I just wanted to show you where it is in the spreadsheet and then also what it looks like. Okay.
Sorry.
No stress. It's a question that I'd ask as well. Okay. Everybody see PowerPoint again?
Yes.
Yes. Okay. So from the log derivative graph, which is that one that I just showed you there, you see log of derivative, log of time. And here's my first derivative graph here. Value of log derivative 0.5 is the fracture network is limited and it's a linear flow. So where you've got a gradient of 0.5, then you've got a limited fracture network. Log derivative of quarter, so 1 to 4, implies a good fracture network, so bilinear flow. That's the one that, remember, I showed you those different colored graphs in FC, or lines on the graph in FC. That's your 0.5, 0.25, and 0.1. So where you've got log derivative of 0.1 or less, that's a very good fracture network. And the aquifer, so you've got radial flow, so flow is coming in from all sides. So here we go, slope of 1 in early time is your well bore storage. And you've got this here, double no flow boundary, single no flow boundary. You see how it flattens out here. And then your closed no flow boundary is where you get a slope of 1 in late time. So that's where you're dewatering it. Yeah, think about what's happening in the borehole. Your water level is dropping. Your drawdown is increasing. So you're going to get this straight line, and that shows you a closed no flow boundary. Then you got your dual porosity dip. So that's why I'm saying your fractures are dewatered. Your dual porosity, you've got matrix flow and fracture flow. So you get a dip where the drawdown decreases over time and then it increases again. So you dewater your fracture there and you start getting drawdown again. Does that make sense?
I'll think about it. Like, you can continue.
Now think about what the graph is showing. It's showing your derivative of your drawdown on the y-axis. So your drawdown will increase when it's dewatering. So water is going out faster than it can come in. Then it'll stabilize when you get to a fracture or a water strike where you're starting to get equal to your pumping. Then you dewater that and it'll increase again. So just think about what's actually happening in the borehole while you're pumping it. Okay, but read that Van Tonder paper. That summarizes it very well. Let me just check in. Okay. So then I'm going to go back to Excel now. And just show you, we'll go through this FC example together. Okay, everybody see Excel again?
Yes.
Cool. Okay, so here it tells me I've got a very good fracture network. Now we're going to go to this Cooper-Jacob method where you fit your line graph here. Now, the way it fits in the newer Excel is quite cumbersome. You see, here's my Y and my X for 0.1. So you'll see if I move that, it moves around. And then the Y as well. You can see that moves around. So it is quite cumbersome, but try to fit your line as best as possible. Because otherwise you can just type it in, but the trick is to type it into this K7. If you type it in here, it doesn't do anything. You see there. There's my X0. There's my Y, no, that's my X1. Then Y0. So you can type it in manually if you want to here. That's just to fit your line. So I'm going to put it back on 5.7. Yeah, so then it calculates my transmissivity and my sustainable yield with no boundaries, 1 no flow, 2 no flow, or completely closed. Gives me an average sustainable yield of 2.97 liters per second. So that's the Cooper-Jacob method. You just fit your line like you would if you were interpreting for transmissivity. Okay, then here is the FC method. Yeah, this is the sort of unique method that the Free State University developed. So you've got your estimated effective borehole radius. This is your extrapolation time from the data sheet. So 2 years, if you type in 20, that'll change to 20. Effective borehole radius. You can calculate it on this RE sheet, but typically you just leave it as the default. Then your Q, your pumping test Q, which is what you've put in at the data sheet. Same as available drawdown on your data sheet. And your effective recharge. That is if you know what the recharge rate is at the site. You know, you've got 20 millimeters per annum. You can put in 20. You see the units here are 20. But to be truly conservative, you want to leave that as 0. Yeah, does anybody have an issue or a question about why you leave recharge as 0? No. Okay, so watch what happens if I put recharge in. You see my average is 1.92 now. So if I put 15 millimeters, it almost doubles. Yeah, look at that. If I've just got 15 millimeters recharge per annum. Yeah, I mean, look at that. So to be conservative, leave it as 0. Maximum derivative, it calculates off of the derivative charts. Second derivative as well. These ones you just leave as default, unless you really want to go into the maths, yeah, which I don't usually do. Then your aquifer thickness, you decide based on your drilling log, your borehole log. Is it a fracture where it's like 5 meters thick zone, or is it 20, 30 meters? You decide that based on your drilling log. And then it estimates your storage, and it even says, yeah, the estimate can be wrong. So that's where you need an observation borehole during your pump testing, or you can use RPT solve. Yeah, that's the recommendation of FC, but I personally just leave it as default estimate. Okay, then here's your basic solution again. No boundaries, then your 1 no flow boundary, 2 no flow boundaries, then a closed no flow boundary. And it gives you your average here. I'm not going to go through the advanced solution because personally I've never used it. Yeah, usually the basic solution is good enough and you don't have enough data really to do advanced solutions. So everybody sort of okay with the data that you put into this FC method, the basic method?
Yep.
Yep. Okay.
Yes.
Yeah. Great. Look, it's pretty straightforward. So I'm not going to go into the maths and that stuff because that just confuses everybody, including me. So this is the way they've built it and it's been accepted. So I'd rather just focus on teaching you how to use the software. The other one that we use is the inflection test, which is what we mentioned in about determining your available drawdown. You can see here, there's my inflection point. You can see it's on a log time and a linear drawdown. So it goes and then it starts increasing. It looks a bit, it just goes up. Similar to here where you've dewatered your fractures. As you see, it's stabilizing. Klingiwe, this is what I was saying on the derivative graph. You've got a fracture that's yielding a decent amount of water. Then you dewater that fracture, so you drop down your water level. Then the fracture starts to almost meet your sustainer or your pumping yield. Then you dewater that fracture. Then here you've got another fracture that's a bit higher yielding than these ones because it lasts longer. And then here you've dewatered that fracture and you're going down towards your main water strike or your pump inlet.
No, I see it.
Great. Always take a step back from the data and think about physically what is it. It's a borehole with water going in from the geology and being pumped out by the pump. And then think about it in those terms. Forget about the maths and the graphs for a second and just physically think about what it is. Yeah, that helps.
No, thank you. I see it actually.
Yeah, no, once you see it and you think about it in the terms that suit you best, then it makes sense. Yeah, everybody, like I like the maths, but some people like the physical side, some people like the graph side. So it's just finding what talks to you, you know. Okay, so again, here as you move the dot around with this, it's not making a big difference here because you're in the 1,000 to the 10,000 on the log cycle. So you can drop it all the way down there. See, look at how it changes my results as I go along. I'm going to put it back on, what was it, 1785. Yeah, there we go. But you see here again, it's a lot higher than the other estimates. So I don't like this one because there you might have another fracture hanging around here. You know, this might be completely dewatered and this doesn't recover. So I personally don't like this inflection method. Okay, I'm going to ignore all those. Then we're going to go to the summary. You see here it's got the check boxes for the basic FC method. That's the average yield that it's calculated. The inflection point, that's the average. Cooper-Jacob, I want that one. FC nonlinear, and then the Barker method. Yeah, so that Barker method is here. I don't use this one that often, but the way you can adjust it as well. You see there's my K, that flattens my curve. The higher it goes, the flatter my curve gets. And then your storage, your thickness here, and then your N. So again, I don't use this one, but you can fiddle with it if you want it. So I'm taking the average as FC nonlinear, the inflection point, Cooper-Jacob, and basic FC. So it gives me an average of 2.9. Then I just like to type in this one manually. I just say equals that average. And that one is for 24 hours a day pumping. So that is flat out pumping. I mean, you're not going to do that on a site. If you know, that's just not practical from a power perspective and a maintenance perspective. So typically you'll do 12 hours of pumping, 12 hours on, 12 hours off. And you see how it increases my yield. So for 24 hours, it's 2.9. And for 12 hours, it's 4.1. Everybody see how the program does that?
Yes.
Cool. And you see, if I don't want, like if I don't trust this inflection point result, I just turn it off. Yeah, then it adjusts that. But just do this correction, just say equals, and then choose this average cell. Because for some reason in the FC sheet, it doesn't do that. Yeah, and get a feel for your site, because if you've done your pump test at 1 liter a second and it's dewatered the borehole, your sustainable yield is not going to be 3 liters a second. Something has happened in your data interpretation. So be realistic. Your sustainable yield is generally not higher than your pumping test yield, unless you're in a caustic system or something like that. Okay, so always go back to your gut feeling. If you don't trust the data, interrogate the data. Okay. Is everybody happy with FC?
Yes, I'm happy.
Yes.
Thank you, Matthew.
Yes.
Great. Any questions about, this? Because this is just a software package. You still have to fiddle with the data. You still need to see if you trust the data or not.
I'm just curious to know if are there any other softwares, like specifically in South Africa, that are similar to FC, or is like FC the like go-to god when you wanna do sustainable yield?
Yeah, my
Or
personal
pumping test data actually.
And my personal experience, I was trained in varsity on FC. I've used FC on all of my projects. I've used those AENV equations that I showed you in the beginning. I've used those as well, and they've been fairly successful. And what I mean by that is that the pumps that we installed based on those calculations didn't burn out.
Okay.
And there wasn't any negative impacts to date, and that was about 5 years ago. So to date, there hasn't been any issues with those equations. Okay.
I see.
And like we discussed in the aquifer testing presentation, the way the farmer tests, they do it. They buy a pump, and then they sort of choke the pump and vary the rate until the water level stabilizes. And that's how they get their sustainable yield. So there are ways, but this is a sort of accepted scientific way to do it.
Okay, thank you.
Okay. Any other questions before we move on? No. Okay, I'm gonna go back.
Matthew,
Yes.
sorry. You said something about encaustic environments. I didn't catch that. The sustainable yield is usually higher or lower than what?
Your pumping rate. For example, if you're in a big caustic cavern and you're pumping at, like I've had it where we pumped at 86 liters a second for 5 days, and we had 0.3 meters drawdown, which recovered in 30 seconds when we switched the pump off. So the yield that we could pump that ball at was higher than the pumping rate that we used in the test.
Oh, okay. Okay.
Yeah. So in general, we want to, when we do a pumping test, a constant discharge rate test, we want to stress the aquifer. We want to stress it for as long as possible, but we do want to stress it. We want that water level to be dropping down so that we can see its reaction to pumping.
Yeah.
Well,
okay. Thank you.
cool. No worries. Okay, I'm going to go back to the PowerPoint slide. There. Everybody see PowerPoint again?
Yes.
Great. Okay, so can anybody tell me the difference between a safe yield and the sustainable yield? Nobody. Okay. So your safe yield, according to the Groundwater Dictionary on the Water Affairs website, is the maximum rate at which water can be removed from a borehole without causing an unacceptable drawdown or change in water quality within the aquifer. In the glossary of statistical terms, the extraction level of a renewable resource which does not exceed the growth. So if you put that in groundwater sort of terms, that is an abstraction rate which doesn't exceed the recharge rate. And here's just a link for those. Yeah, on the Water Affairs website, the safe yield and the sustainable yield is the same definition. But that I don't fully agree with. If you think about sustainability, your sustainability is comprised of your people, the economy, and then the environment. So you need to look at the sustainable yield as something that helps the people and the economy. So it's got economic and social benefits, but does not negatively impact the groundwater environment or the surrounding environments. Does that make sense? The 3 pillars of sustainability.
Yes.
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 Yeah, great. So you've calculated your borehole yield, that's fine, but that may not be the sustainable yield. So that's what we're going to go through now, is just how to determine if that yield is sustainable for your site. Remembering our pillars of sustainability, the social or people, the economy, and then the environment. So groundwater sustainability is defined as the development and use of groundwater over an infinite amount of time without causing unacceptable consequences to the environment, society, or economy. So the safe yield definition was negative impacts on the aquifer, whereas the sustainable definition is the aquifer, which is part of the environment, the rest of the environment, and then society and the economy as well.
So in terms of the sustainable yield, would you really like, does it really like not make sense, but like, is it really like a good idea, in inverted commas, to really say that it's a sustainable yield? Because they're talking about an infinite amount of time, but like, really, is really that possible? Is that really possible? Because sometimes you can have a borehole and then your neighbor decides to have a borehole, and then now it affects your yield, and then the sustainable yield that you initially thought was sustainable is no longer sustainable anymore because the neighbor now decides to do their own thing. Like, does really sustainable yield exist, or is it sustainable given the conditions that we have at this moment today now, like
exactly. It's like any scientific study or scientific finding. If conditions change, it's like most physics experiments and stuff exists in a vacuum. Sustainable yield, but I understand what you're saying about the neighbor, but if my car can do 0 to 100 in 6 seconds, but then someone rides into me and knocks off one of my wheels, that doesn't mean my car can't do 0 to 100 in 6 seconds. It means my car is broken. You know what I mean? So with sustainable, that's why we do the extrapolation time on FC. And remember, your pumps have a life cycle. Your pumps last 10 to 15 years. Your borehole itself has a lifespan of 10 to 15 years. So the infinite time is just it's a choice of wording. It's in theory that this should be sustainable forever to make it sustainable.
Okay, I hear you.
And that's the whole sort of argument with sustainability as a concept. Never mind groundwater sustainability, that's green electricity, and it's an argument that comes up, is that what happens if, and you can look at what ifs until the sun goes down, but we do need to sort of move forward and do the best we can with what we have.
Okay, thank you.
Okay. So the sustainable groundwater yield should be defined in terms of the entire hydrological cycle and with a long-term approach, taking into account potential climate change impacts or changes to other aspects of the hydrological cycle. So that's if your rivers dry up, or if the wetlands increase or the rivers flood, etc. So you want to look at your entire water cycle. And then the water balance is where inflows and outflows, in a steady state, inflow equals outflows. And then typically your inflows and your change of storage is equal to your outflows. So that's the water balance. Now, the sustainable yield of a borehole needs to take into account, according to Kalf and Woolley, economic issues, social issues, and environmental issues. That's again your 3 pillars of sustainability. In the groundwater regime, the groundwater extraction regime measured over a specified planning time frame that allows acceptable levels of stress and protects dependent economic, social, and environmental values. So if you can, I'd suggest you read this paper, if you can get hold of it. It goes through the concepts of sustainable groundwater development quite nicely. And it's written in the Australian environment, which is fairly similar to the South African one, you know, geologically and climate-wise. Now we'll go through how to actually do the sustainable yield calculation. Now that we've done the sort of definitions. And this is a really nice graphic of all the different factors that influence your sustainable groundwater management. So you've got your drivers of change, which is your sustainability of groundwater, the resilience to climate change, the adaptation and transformability of the groundwater resource. And then technological factors, is there new pumps that are available? Is there new treatments that are available that make things accessible that weren't accessible before? How complex are they? How durable are they? How costly are they? Environmental factors such as protecting your ecosystem, biodiversity of the area. Economic factors, obviously if you're going to have to charge $10 per liter of water to earn some money, if you're selling the water, then it's not economic. People aren't going to pay that, not now anyway. But economic takes a big part of water supply. And social factors, how complicated is the system? Oh, sorry, do people want it? A lot of African cultures, I've found, like in East Africa and Central Africa, the guys don't trust groundwater. They don't want water from a borehole. That's, I'm not sure if anybody's encountered that in South Africa or anywhere that they've worked. But I know in Tanzania, they weren't keen on a borehole at all. They wanted river water and that was it. So if the people don't want a borehole, don't drill a borehole. And then from all of these factors, you're going to get new approaches to support your sustainable use and management of groundwater. And again, if you can, I'd suggest you get this paper because it's quite an interesting paper, because Qatar is a semi-arid to arid environment, a little bit drier than us, but quite interesting nonetheless. Okay, so the water budget approach that I typically use in my water use license reports, you can also call this a groundwater reserve determination. Do you guys still learn the GRDM method in varsity?
I didn't. I don't know what it is.
What does that stand for?
Groundwater resource directed measures.
Well, I'm still in varsity, so maybe it's still coming. I don't know.
Okay.
No, I don't know it.
Okay. Lizelle, do you guys do it?
Yes, I think we did. I just can't recall.
Okay. Rachel?
No, I haven't heard of it either.
Really? Ricky doesn't make you do it?
No.
Oh dear. Okay. Now, well, I'll go through it quickly. This is also the water budget approach. It just shows you that your yield is sustainable or not in the long term. Can your aquifer system and your groundwater environment sustain your calculated borehole yield? So the way we do that is we do it in the context of a basin or a sub-basin, or in your groundwater environment. So that we call our unit of analysis. So these are boundaries to my groundwater flow. So I've got a perennial river here. It's like your model boundaries, which we'll go through on next week or the week after with the modeling section. So groundwater is likely on this site to flow into the river and then into the river. So I've got a boundary to groundwater flow there and here as well because of a river. And then here is just a topographic break. Groundwater is not going to flow up the hill and down the hill again. So there's a break there. Groundwater will flow down into my site here. And here is a quaternary catchment boundary, which I assumed was representative of groundwater flow as well. Okay, so you choose your model boundaries or your catchment boundaries for the site. This is my environment where groundwater is going to come into my borehole. That was called strong borehole. This dark blue dot. Does that make sense to everybody?
Yes.
Cool. Okay, next step, you calculate your basic human needs assessment, which you get from your census databases, and you look at it, how many people are within my unit of analysis. Then you take that population number, multiply it by the 25 liters per person per day, which is, I think it's the UN or the WHO bare minimum for people. So if I've got 100 people, it'll be 2,500 liters per person per day. Then you calculate that need per annum. And then you do groundwater contribution to base flow. You can do that by hydrograph separation if you have hydrographs, which is your river flow rates over time. Or you can just get it from the WR 2012 or GRDM databases, where it'll tell you for this catchment. There's a question. Okay, Lichle, how do you determine the boundaries? Your boundaries are the boundaries to groundwater flow. So we'll go through it in detail with the modeling section, but it's where like groundwater won't flow across this perennial river in this environment. So that's a boundary. Then it won't flow across this channel here. So that's a boundary. Then here is a topographic divide because groundwater can't flow uphill and then downhill. So all of the water on these boundaries impacts on my borehole, and everything outside has no impact on my borehole, and my borehole can't impact it. Does that sort of explain the rough idea of boundaries?
Can you hear me?
Yes.
Okay, it does explain. I do get the boundary on the river boundary and the one at the bottom, but it's the other two that I don't get how you would define those boundaries. Or would we go through that when we're doing the modeling section?
It's environment specific. You know, on this one, we had a non-perennial channel here and a geological contact. So you've got like a hard quartzite here and then a sandstone here. So it's unlikely that huge amounts of water are going to go through into the quartzite from the sandstone.
Oh, all right.
Okay,
thanks.
so it's site specific, but we'll go through it with the modeling session.
All right, thank you.
Okay. So we've got unit of analysis, then we do our basic human needs assessment and the groundwater base flow contribution. Okay, then we have to define our groundwater recharge for the unit of analysis. You do this by the chloride mass balance method if you have it, or you look at your maps, your Vector map, databases, any regional databases, your soil maps, groundwater harvest potential, all previous reports for the region or near to the site. the more data you have, the better. If you can get 100 different recharge points and take an average, that's great. Yeah, it'll help you defend your recharge value that you assign. There's just the recharge method, or the chloride mass balance method for recharge calculation. Then existing abstraction is also important. Yeah, that you'll get from your hydro sensors or from the regional databases such as WARMS or the WR 2012 database. Yeah, that's who's pumping out of this aquifer already. Is my neighbor pumping? That relates back to the question we had earlier about sustainable yield and neighbors, etc. So when you do the water budget, you take into account the existing abstraction. And if your neighbor wants to drill a borehole, he should take into account your existing abstraction. Yeah, then you have your proposed abstraction, which is your calculated borehole yield. Oops. Okay, so is everybody with me in terms of what we need to get together for our water budget?
Yep. Yes.
Yeah.
Yes.
Pretty straightforward. Yeah, then we calculate the groundwater component of the reserve, which is the part of the groundwater resource which sustains both human needs and contributes to environmental water requirements, such as your base flow. Now, your base flow, that's why the base flow calculations are important. So the base flow could be to a river or to a wetland or to any kind of surface water feature. If groundwater feeds that feature in the dry season or whenever, that is base flow. So the groundwater component of the reserve is calculated by taking your basic human needs plus the contribution to base flow, and you divide that by my total recharge, and that'll give you a percentage. So that is the percentage that you cannot touch. You need to have groundwater to meet basic human needs, and you need to have groundwater that doesn't take away from the existing environment. So that's your base flow. Yeah, because realistically, groundwater doesn't contribute to the environment other than base flow. Does that make sense to everybody?
Yes, Matthew, it does.
Cool. So then you determine the overall sustainability of your calculated yield in terms of the allocable groundwater reserve. So I've got my area in meters squared of my unit of analysis, my mean annual precipitation. And I use those two to calculate my volume of recharge per annum. Yeah, we use the mega cubic meters per annum. So that's million cubes per annum. So I've got 0.69 recharge. My basic human need was 0.001. Groundwater contribution was 0 because that's a losing river on this site. So the river feeds groundwater, not the other way. The existing abstraction in the catchment was 0.1, which was actually, it was my client's other borehole. And then the proposed abstraction was 0.28 mega cubes per annum. So then I calculate my groundwater reserve. So my total recharge is 0.69, and my groundwater reserve was 0.13 of that 0.69. So that is basic human need plus my contribution to base flow. Gives me 0.13. So that is what I cannot touch out of that recharge component, which leaves me with an allocable reserve of 0.59. Does that make sense to everybody?
Yep.
Cool. So then what I do is I take my proposed abstraction rate that I've calculated and divide it by the allocable reserve, and I can see it's less than 50% of that allocable reserve. So do you see that means that my calculated borehole rate is sustainable, because I'm not getting up to the 90% of what's left over. Like, there's still more than enough water to meet the environmental requirements and the social requirements if they increase. So there's my sustainable yield. I've proved that my borehole calculated yield is actually sustainable in the context of the site. And you can use this to run different scenarios. So for example, if I had to halve the rainfall, which means I'll halve my recharged groundwater, then my calculated yield becomes 113% of the allocable reserve, which means it's not sustainable. So therefore, if it's in a drought-prone area, or if your climate change data suggests it's going to go into a drought, you need to adjust your calculated yield to 75%, so 0.21 instead of 0.28, to be sustainable, to be less than 90% of your allocable reserve. Yeah. So you see, it's a fairly straightforward concept to calculate your budget and say, this is what's important for the environment. This is what I want to take out of it. Yeah, is it sustainable or not? Everybody agree that it's simple, or is it confusing?
It makes sense.
Yeah, cool. So yeah, that's the end of it. So are there any questions about your sustainable yield, safe yields, FC, what we've gone through today?
Matthew, that FC program seems very complicated. Like, it seems very complicated. But one day I'll download it and like try working on it.
Yeah, look, it's not complicated at all. You literally input your data, and then you can either you can choose what you want to do. You can make it as complicated as you want it to be. You know, it's not. We can maybe do an example on Thursday when we go through the task. Yeah, but you'll see it. It's really, it depends. If you want to do all of the methods, it's complicated. But if you just want to do the Cooper-Jacob and the basic FC, it's not that bad.
Yeah, the Cooper-Jacob, that I understand, and the basic, I understand. But the rest, I did not hear what you said. I did not understand what you said.
How do you mean?
On the Excel spreadsheet, there was, I don't know which data set you were working with, what you were calculating. I think it was the interception or something like that, or inflection, or yeah,
the inflection point, yeah.
Yes.
Okay. I think let's go through it with the other aquifer testing on Thursday, and then you'll see it'll make a little bit more sense.
Okay, thank you.
But don't stress about it. Don't be scared of it. You know, we've got Control Z, undo. It's not an issue.
Okay, thank you, Matthew.
Cool. Any other questions?
Hi, Matthew. I just wanted to ask if the slides will be available just for me to look over everything again and get those papers.
Yep, definitely. I'll upload it to the website tomorrow.
Okay.
And then you can just go to the company website and go to the download section.
Okay.
All of the slides are there, and then all of the previous slides are also up.
Oh, great. Thanks so much.
Cool. No, I mean, if there's any questions, just send an email through, and yeah, no worries, we'll go from there.
Thanks.
Cool. Any questions on sustainable yields and that? Stephen?
No, I just wanted to say thanks, Matthew. That was great today. Thanks a lot.
No, thanks, guys. Yeah. Lingiwe, any questions?
No, this one has, yeah, well, it kind of doesn't have anything to do with today, but the whole process of from like the first from the beginning up until the end, like in terms of producing the reports, in terms of doing the pumping test and whatnot, how long generally does it take you to do like the entire thing for you to actually know everything about that borehole and the yield and the pump that you need to get. And yeah, until let's say people use it for like human consumption, like for everyday basic needs. Like how long generally does it take you?
Yeah, look, I mean, a thumbsuck for something that's within 100 kilometers of the office, I would say 4 to 6 weeks, including about 10 working days for the laboratory results. And also it depends on your client. If your client wants you to do one thing at a time, then it can take up to 8 to 10 weeks. And then if it's a faraway site, that obviously takes longer because you've got to drive out to do the geophysics. Then you come back to the office and interpret. But maximum, you're looking at probably about 3 months, so 12 weeks.
Okay.
Yeah, and minimum, you're looking at 4 weeks.
Okay. Interesting.
Yeah, look, sometimes projects come together, but other times they fall apart.
And then when they fall apart, is it on you? Like, are you, okay, obviously it's on you. There's more like bigger parts on you. But like, do you like have to start all over for you to actually fix where the issue is or where the problem is?
It depends what the issue is. Sometimes, a drill rod will get stuck in a hole. And then the driller will tell you, you need to pay for it. And the client will say he's not paying for it. And then you're going to sit there fishing for a drill rod for 3 weeks. Other times you drill a dry borehole and the client doesn't want to pay you, or the client makes you go drill another borehole. And there's so many things that can go wrong from a personal or a personnel perspective. You can have an incident on site and your site gets shut down. You could have it where, I've had it where they drilled into dolomites and then the dolomites collapsed on the rod and they lost the hammer, the rods, everything. And the driller spent 3 weeks trying to get his rods back. So every site is different. You've just got to, I've said it before, you've got to manage your liabilities in your contract. You've got to make sure that everybody's responsible for their own part of the world. Driller must look after drillers and drilling equipment, and you must look after the site and the client's interests.
Yeah, I hear you. Yeah. Thank you.
Read the contracts, because a lot of drillers in the initial proposal, they'll say to you, you are liable for the equipment that gets lost or damaged. Negotiate that and say to them, listen, this is a hard rock environment, so you are going to lose bits. The bits are going to get worn, but I'm not going to pay for a new drilling bit. Be upfront in your negotiations.
Okay.
Yeah. Don't let it be a surprise later when there's a couple $1,000 on the line.
Yeah. Cool.
Cool.
Matthew, I want to ask, how much does the whole thing cost, from the hydro sensors all up to the sustainability and then the reporting part, like the whole project, when including everything? How much, like generally, does it cost?
Look, your costs, including drilling, aquifer testing, lab costs, everything, and your pumps, you're looking at anywhere between 150,000 and 250,000 Rand for one borehole. That's if you do everything top of the line. You do proper drilling, proper casing, but you can get away with 120,000 to 150,000 Rand.
Oh, okay. Thank you.
Your main cost is your drilling. You get drillers that charge anywhere between 300 and 600 Rand a meter. But if you go into larger diameters, you're looking at potentially 1,000 to 1,200 Rand a meter drilling cost.
Oh, okay. Thank you.
Anybody else?
Just to comment on Bibila's question, actually. We are actually, well, where I work for the Department of Water Affairs. So we are actually doing a borehole like custom model, and it would actually be very helpful if, you know, I can send some of my stuff to you, Matthew, and then you just like give me an idea of like, because we already have the model, but we are like kind of refining it, because the Bibila's question of how much, actually, like a lot of people are scammers. Well, not scammers, but like they will scam you, you know, they will charge you like millions and millions, especially if they're charging like directly the government. They charge millions and millions when it's not really like that much. So yeah, Bibila's question is very important, and I'm working on it. So yeah.
No, that's interesting. Yeah, look, if you can share it, that'll be great. You know, because I know a lot of, I can't remember what it was for, but there was like a scandal where the drilling contractors were charging like R1 million a borehole for water affairs. I think it might have been Cape Town with the drought relief. Yeah, there was a big thing last year or the year before.
Was the year before?
Yeah, because it happens. And the thing is also drillers will charge, like I know the water affairs drillers, I've heard stories about them. I don't think you have a drilling department anymore. But, you know, the old guys would tell me stories about, because they got paid per day, not per meter. So they would take 20 days to drill one borehole.
Imagine.
Yeah. So, you know, most drillers get charged or get paid per meter. So the more they drill, the more they get paid.
Yeah, no, but I'll definitely send my model, and then you can check it out and see if it actually makes sense.
Yeah, thanks. Yeah, just clear it with your bosses first.
Oh yeah, I did.
Okay. Yeah, I don't want you guys sharing stuff you're not supposed to.
Yeah, I know how that important is. How important that is also.
Yeah. No, but thanks. I'd appreciate that. I think it'll be nice for the group. You know, maybe you can present it to everyone and explain it a bit.
Yeah.
Yeah, awesome.
We'll do that.
Thank you. I'd really also appreciate it.
Great. So everybody happy? We're going to carry on Thursday again. We'll go through the task and all that stuff.
Yes, thanks.
Awesome. Okay, so thank you very much, guys. Thanks for joining us, and I hope everybody learned something about the sustainable yield and the groundwater resource development cycle over the past couple of days. And we'll pick it up on Thursday again.
Bye.
Thanks a lot, Matthew.
Cheers, guys. Have a good week.